The universe is 13.8 billion years old, and right now, a telescope floating 1 million miles from Earth is staring at light that left its source before our planet, our star, or even our galaxy existed. We are going to find out exactly how that is possible. And the answer involves a universe that stretches light into invisibility, a mirror made of gold, a toxic metal that almost nobody has heard of, and a machine that had to fold itself like origami just to fit inside a rocket. If you enjoy what you are about to hear, hit like and subscribe. It genuinely helps. Take a breath. This one goes deep. Every time you look at the night sky, you are looking into the past. Light travels fast, faster than anything in the universe. But even light takes time to cross the distances between stars and galaxies. When you look at the moon, you are seeing it as it was just over a second ago. When you look at our nearest stellar neighbor, you are seeing light that left home 4 years before it reached your eye. When you look at the Andromeda galaxy with binoculars, that faint smear of light departed 2.5 million years ago, when our earliest human ancestors were just beginning to walk upright on a continent called Africa. The farther away something is, the further back in time you are seeing it. This is not a metaphor, it is physics. Distance and time are the same thing when light is your messenger. Every telescope ever built is, in that sense, a time machine. It does not move through time. It receives ancient light and decodes what that light looked like when it left. The larger the telescope, the more light it can gather, and the fainter and more distant the sources it can detect. The James Webb Space Telescope pushes this to its absolute limit. Its primary mirror is 21 feet across, roughly 6 times the collecting area of the Hubble Space Telescope. That size alone lets it gather far more light than any previous space instrument, reaching objects so distant and so faint that Hubble could not detect them at all. But size is not the strange part of this story. Plenty of telescopes have been built bigger over time. The strange part is what kind of light Webb was built to see, and why that specific choice required the entire machine to be redesigned from first principles. Because the light Webb is chasing, the light from the very earliest galaxies, formed just a few 100 million years after the universe began, does not look like light anymore by the time it reaches us. Something happens to it during the journey, something that the universe itself does to every photon that travels across expanding space. And once you understand what that something is, every other engineering choice Webb's designers made starts to make sense in a way that feels almost inevitable. The universe, it turns out, is not a passive backdrop through which light travels unchanged. It is an active, expanding thing, and that expansion does something to light that changes everything about how you build a telescope to see the beginning of time. The answer starts with a question most people have never thought to ask. If the universe is expanding, what exactly is expanding? And what happens to a wave of light when the space it is traveling through gets bigger while the light is still inside it? The answer to that question is what turned ancient visible light into something entirely different. Something invisible, something that required an entirely new kind of telescope to detect. And that is where the story gets genuinely strange. Imagine a sound wave moving through a room. Now imagine the room stretching, getting longer, wider, taller, in all directions at once, while the sound wave is still traveling through it. The wave would stretch too, its wavelength would lengthen, and a longer wavelength means a lower pitch. The same sound, traveling through a room that grew during its journey, arrives at your ear lower than it left its source. Light works the same way, and the universe has been expanding since the moment it began. This is confirmed science. It is one of the most solidly established facts in all of cosmology. Edwin Hubble confirmed it observationally in the 1920s when he noticed that galaxies are moving away from us and that farther galaxies are moving away faster. The universe is not exploding outward into empty space. Space itself is growing. Every point in the universe is moving away from every other point, like dots on a balloon being inflated. Now, consider what this does to light. A galaxy 13 billion light-years away emitted light 13 billion years ago. That light has been traveling through space ever since. But the space it has been traveling through has not stayed the same size. It has expanded enormously during those 13 billion years. And just like the sound in the stretching room, the light wave has stretched along with it. The wavelength of that ancient light has grown enormously. Scientists measure this stretching as redshift, a term that describes how the light shifts toward the longer, redder end of the visible spectrum as it travels. The farther away the source, the more the light has stretched, and the more it has shifted toward red. Now, here is where it gets truly strange. The oldest light in the observable universe, from the earliest galaxies that formed just a few 100 million years after the beginning, has stretched so far that it has left the visible spectrum entirely. It has been pulled so far toward longer wavelengths that it is no longer visible light at all. It has become infrared light, the same kind of radiation your body gives off as body heat, the kind of energy emitted by a warm cup of tea or a slightly heated metal surface, the same type of radiation that night vision goggles detect to show warm objects in the dark. This means that the very oldest, most distant galaxies in the universe are completely invisible to any telescope built to observe invisible light. They are not too faint to see. They are radiating in the wrong part of the spectrum entirely. Hubble was looking in the right direction, but with the wrong eyes. To see the beginning of the universe, you need a telescope that sees infrared light, one specifically designed and optimized for it, from the mirror to the instruments to the orbit. But infrared light creates a problem that no engineer had fully solved before Webb, a problem so fundamental it almost made the mission impossible. Infrared light is heat, and that means the telescope itself is a threat to its own mission. Here is the problem in one sentence. Infrared light is heat, and every warm object in the universe emits it. Your hand glows in infrared right now. A rock sitting in a field glows in infrared. A mirror on a space telescope, sitting in the warmth of sunlight, glows in infrared so brightly that it completely overwhelms the faint ancient signals Webb is trying to detect. Think about trying to see a single candle burning on the surface of the moon. Now imagine that someone has placed a floodlight directly in front of your eyes. The candle is still there. The light from it is still reaching you, but you cannot see it because the light source right in front of you is 1,000,000 times brighter. That is what happens when an infrared telescope is warm. Its own mirror becomes the floodlight. The ancient signals from 13 billion-year-old galaxies are drowned out completely by the thermal glow of the instrument itself. Hubble operates at roughly room temperature in the shade of space. For visible light, that is perfectly fine. Visible light mirrors do not need to be cold. But for infrared, a warm mirror is a disaster. The solution was straightforward to describe and extraordinarily difficult to achieve. Make the telescope cold. Not cool, not chilly. Cold in a way that almost has no everyday equivalent. Webb's primary mirror needed to operate at around -364 degrees Fahrenheit. For context, the coldest naturally occurring temperature ever recorded on Earth's surface is around -129 degrees Fahrenheit. Liquid nitrogen, which freezes things almost instantly on contact, sits at -320 degrees Fahrenheit. Webb needed to go colder than liquid nitrogen and stay there indefinitely in the vacuum of space. At those temperatures, materials behave in ways that engineering textbooks from 50 years ago could not reliably predict. Metals contract and can crack, lubricants freeze solid, electrical connections fail. Glass, which has been the standard material for telescope mirrors since the time of Galileo, becomes dangerously unstable because different parts of it contract at slightly different rates, warping the precisely shaped surface into something useless. Webb's designers needed a mirror that could survive being cooled from room temperature all the way to -364 degrees without changing its shape by more than a few billionths of a meter, and then stay at that shape exactly for years. Glass could not do it. Standard aluminum mirrors could not do it. The materials that had served telescope builders for centuries were, at Webb's operating temperatures, completely inadequate. This forced a search for something new, something that almost nobody had ever used to build a large mirror before, something that, when engineers first proposed it seriously, raised eyebrows across the astronomy community. And finding it required running a formal competition between two different materials, cooling both of them to the edge of what was physically achievable in a test chamber, and watching to see which one held its shape and which one failed. Only one of them passed, and it was not the one most people would have predicted. The competition was simple in concept. Build two prototype mirrors, cool both of them to Webb's operating temperature in a vacuum chamber, measure their surfaces before and after. Whichever one held its shape with the least distortion would become the material of choice for the most ambitious space telescope ever designed. One prototype was made from glass, specifically a type called ultra-low expansion glass that had been developed precisely for applications where thermal stability was critical. It was the favored material going into the test. It had the weight of tradition, decades of use in precision optics, and a manufacturing supply chain already built to handle it. The other prototype was made from beryllium. Most people have never encountered beryllium in daily life. It sits at the top of the periodic table between lithium and boron, atomic number 4, one of the lightest structural metals that exists. It is extracted from mineral ores found in a few locations around the world, processed through methods that require strict safety controls, and used almost exclusively in specialized aerospace and defense applications, where its unique combination of properties justifies its cost and difficulty. Beryllium is extraordinarily stiff for its weight. A beryllium rod the same size as a steel rod would weigh roughly 1/3 as much, but be significantly stiffer. For telescope mirrors, stiffness matters because a mirror that flexes under its own weight or under the tiny forces of thermal expansion produces blurred images. But the property that made beryllium the candidate for Webb was something more specific. Its coefficient of thermal expansion at cryogenic temperatures is exceptionally low. That technical phrase means when you cool beryllium to extreme temperatures, it shrinks very little, and it shrinks uniformly. Every part of it contracts by the same tiny amount in the same predictable way. Glass, cooled to the same temperatures, contracts more and does not do it uniformly. Different regions contract at slightly different rates depending on microscopic variations in their composition. The result is a surface that, after cooling, is subtly but measurably different in shape from what it was at room temperature. For a telescope that needs its mirror surface accurate to within a fraction of the wavelength of light it is detecting, that change is catastrophic. The test confirmed this. The ultra-low expansion glass prototype failed to hold its shape at cryogenic temperatures to the required precision. The beryllium prototype held almost perfectly. The decision was made. Webb's primary mirror would be made from beryllium, but beryllium brought its own serious problem, one the designers knew about going in and had no clean way around. Beryllium is mildly toxic. Inhaling its dust causes a condition called chronic beryllium disease, a permanent and sometimes fatal lung disorder. Every facility that worked with beryllium for Webb operated under strict hazardous material protocols. Workers wore respirators. Rooms were sealed and pressurized negatively so that no dust escaped. The material that would let Webb see the beginning of the universe required treating every workshop that shaped it as a controlled, hazardous environment. And there was one more problem with beryllium, a fundamental one that no amount of polishing or shaping could fix, and that made a completely different material absolutely essential before a single photon of light could be reflected. Beryllium is cold, stable, lightweight, stiff, everything a telescope mirror needs to survive the journey to space and the operating conditions at the second Lagrange point. There is one thing it cannot do. Beryllium is a poor reflector of infrared light. At the wavelengths Webb needs to detect, it absorbs a significant portion of what hits it, rather than bouncing it toward the instruments. For a visible light telescope, this would not matter at all. For an infrared telescope trying to detect signals from galaxies 13 billion years away, a mirror that absorbs infrared is almost useless. Imagine building a radio telescope with an antenna made of a material that absorbs radio waves. The engineering of the structure might be perfect. The positioning might be flawless. But if the collecting surface absorbs the signal instead of focusing it, the whole instrument fails at its one essential job. That was the situation Webb's engineers faced. The best material for cold stability could not do the thing a mirror is supposed to do. The solution required thinking about mirror coatings. Most large telescope mirrors are not made entirely of one material. They have a structural substrate, the main body of the mirror that holds the shape, and a thin reflective coating applied on top. The substrate provides the strength, stiffness, and thermal behavior. The coating provides the reflectivity. For visible light telescopes, common coatings include aluminum and silver. Both reflect visible light extremely well, but in the infrared ranges Webb was built to observe, neither performs as well as a different element entirely. Gold. Gold reflects infrared light with an efficiency that no other practical coating material can match at Webb's operating wavelengths. The physics behind this comes down to how gold's electrons behave. The outermost electrons in a gold atom are loosely held and highly mobile. When infrared light strikes a gold surface, these electrons oscillate in response and re-emit the energy as reflected light, losing almost nothing in the process. The result is a reflectivity that approaches 98 to 99% across the wavelength range Webb operates in. Silver actually outperforms gold in the visible spectrum. Aluminum is more common and less expensive. But in the specific infrared wavelengths that carry the redshifted light of the early universe, gold is simply the best option that exists. So Webb's mirror became a combination. Beryllium substrate for cold stability and structural integrity. Gold coating for infrared reflectivity. The gold coating on each of Webb's 18 mirror segments is 100 nanometers thick. That is about 1/1000th the width of a human hair, thinner than most soap bubbles. Invisible as a separate layer to the naked eye, but responsible for almost all of the mirror's scientific usefulness. The total amount of gold used across all 18 segments combined weighs less than 2 ounces, less than a typical piece of jewelry. At current prices, the gold itself costs a few $1,000s on the open market. The beryllium substrate beneath it cost hundreds of millions of dollars to shape and polish, which raises a question that points to the most demanding physical process in the entire telescope construction. What does it actually take to polish a metal to the precision that Webb required? And why does it cost so much more than the gold that covers it? Each of Webb's 18 primary mirror segments is a curved hexagon, roughly 4.5 feet across. The curve is not decorative. It is a precise mathematical shape calculated so that all 18 pieces, working together, focus incoming light onto a single point with no tolerance for error. The surface of each segment had to be smooth to within 20 nanometers, 20 billionths of a meter. To picture what that means, if you scaled one of these mirror segments up to the size of the continental United States, the tallest allowable surface bump would be about an inch high across 3,000 miles of mirror surface. Beryllium is a hard metal. Polishing it to that standard is not something a machine can do alone. It requires human technicians working by hand, using tools barely wider than a fingernail, removing material one microscopic layer at a time. The process takes months per segment. After each polishing session, the surface is measured with interferometers instruments that use the interference patterns of laser light to map the surface to nanometer accuracy. The measurements reveal where more material needs to be removed, and the polishing continues. Every session produces beryllium dust, and beryllium dust is toxic. The facilities where Webb's mirror segments were polished were not standard optical workshops. They were controlled, hazardous environments with negative air pressure to prevent any particles from escaping, with workers in respirators and full protective gear, with waste handled according to hazardous material protocols. The entire polishing campaign for all 18 segments, from rough machined block to finished optical surface, took the better part of a decade. Then, each segment went through cryogenic testing. Engineers cooled the finished segment to Webb's operating temperature in a vacuum chamber, the same chamber originally built for testing Apollo program hardware and later modified specifically for Webb. They measured the surface shape at operating temperature. If the shape had drifted from specifications, they adjusted. Then they cooled it again and measured again. The goal of all this was to confirm that the room temperature shape and the cryogenic operating shape were related in a predictable, compensable way, so that when the mirror was polished at room temperature, engineers knew exactly what shape it would take in space. Once all 18 segments passed cryogenic testing, they faced one more challenge. They had to be aligned to each other, not roughly, to within 1/10,000th the thickness of a human hair, so that they acted not as 18 separate mirrors, but as one single, perfectly unified surface. This alignment could not be done on the ground. The mirror would fold for launch, travel 1,000,000 miles, unfold in space, and then cool for weeks before scientists could even attempt to measure its shape. The alignment had to happen in space, remotely, using tiny motorized positioners on the back of each segment, commanded from Earth. Each segment has 6 of these positioners, called actuators, capable of moving their segment by steps measured in nanometers. The process of aligning all 18 took several months after launch, but before any of that could happen, the mirror had to survive something that engineers had spent years quietly dreading, something with over 300 separate ways to fail, and no way to fix any of them from the ground. A 21-foot mirror cannot fit inside a rocket. The largest rocket fairings available at the time Webb was designed could accommodate a payload roughly 14 feet wide. Webb's mirror, fully assembled and deployed, spans 21 feet. The math does not work. The telescope could not launch in its operational configuration. The solution the engineers arrived at was folding. The 18 hexagonal mirror segments are mounted on a framework that can collapse. The central 6 segments remain fixed. The 6 segments on each outer wing, 18 pieces in total, fold inward on hinges, tucking against the central section, so the whole assembly fits within the fairing. When the telescope reaches space, the wings unfold, lock into position, and the mirror becomes a single surface again. This sounds straightforward. In practice, it required solving an engineering puzzle that had never been attempted at this scale before. The folding structure had to be rigid enough to survive the vibrations of launch without shifting the mirror segments even slightly out of position. It had to be light enough not to push the telescope over its mass budget, and it had to deploy reliably in the vacuum and temperature extremes of space, with no human hands available to help if anything went wrong. The mirror folding was just one part of the deployment challenge. The entire telescope was packed for launch. The heat shield, which is bigger than a tennis court when fully deployed, was folded into a package small enough to fit inside the rocket. The secondary mirror, mounted on 3 booms at the front of the telescope, was folded flat against the structure. The tower that separates the cold mirror assembly from the warm spacecraft electronics was retracted. When the rocket released Webb into space, what was floating there looked almost nothing like the telescope in the famous photographs. It was a compact, folded package, everything tucked and bundled and latched, waiting to be unfolded over the following 29 days. 29 days. That is how long the full deployment sequence took. During those 29 days, over 300 separate mechanical events had to occur in the correct order. Each one was a single point of failure. A single jammed hinge, a single cable that did not tension correctly, a single latch that failed to engage, and the mission was over. There was no repair option. No astronaut could reach Webb at its destination, 1 million miles from Earth. The heat shield deployment alone involved hundreds of individual release mechanisms and miles of tensioning cables, all of which had to fire in precise sequence while the telescope was traveling through deep space in a vacuum, at temperatures that swung several hundred degrees between the side facing our star and the side facing away. Engineers had spent years running simulations and ground tests for every deployment step. They had redundant mechanisms where possible. They had rehearsed the command sequences hundreds of times. When the launch finally happened on December 25th, 2021, the team on the ground could do nothing but watch their telemetry screens and wait. What the screens showed, step by step, over those 29 days, was either going to be the greatest success in the history of space telescopes or the most expensive failure. And the most dangerous moment of all was one that almost nobody outside the engineering team had paid attention to. It had nothing to do with the mirror. The heat shield is the part of Webb that nobody talks about. Every photograph shows the golden mirror. But without the heat shield, that mirror is completely useless. The problem it solves is the same one that required the mirror to be cold. Webb needs to operate at -364 degrees Fahrenheit. A telescope that close to our star, even at 1 million miles distance, receives enormous amounts of solar radiation. Without shielding, that radiation would warm the telescope to temperatures far above what the infrared instruments can tolerate. The heat shield is 5 layers of a material called kapton, a thin plastic film used in electronics and aerospace applications. Each layer is coated on one side with aluminum and on the other side with silicon. Each layer is about as thick as a human hair. When deployed, the 5 layers stretch across an area roughly the size of a tennis court, with small gaps between them, so that heat absorbed by each outer layer can radiate away into space before reaching the next one. The physics is elegant. The outer layer, facing our star, absorbs heat and reaches temperatures above 200 degrees Fahrenheit, but it radiates most of that heat back outward into space. The second layer receives only a fraction of what the first absorbed. The third, even less. By the 5th layer, the temperature on the cold side drops to around -390 degrees Fahrenheit. That is cold enough for the telescope to begin approaching its operating conditions, with the cryogenic cooling system handling the rest. Folding a tennis court of extremely thin film into a package small enough to fit inside a rocket, and then reliably unfolding it in space, was one of the most complex mechanical challenges in the entire mission. The folded shield had hundreds of individual membranes, each of which had to unfold in the correct sequence without tearing or tangling. The tensioning system, which pulls the layers taut after unfolding, used miles of cables running through pulleys and over precision-machined spreader bars. Every pulley had to turn. Every cable had to tension to exactly the right load. A single tangle in the layers, even a small one, would have been permanent. There is no procedure for untangling a heat shield in space from a ground control center 1 million miles away. The shield deployment took several days. The team watched each step on telemetry, confirming that membrane after membrane had released and tensioned correctly, that the spreader bars had fully extended, that the whole structure was pulling itself taut in the cold vacuum. It worked. Every step, without a single anomaly, with the shield fully deployed and the telescope cooling toward its operating temperature. The mirror assembly could begin its own months-long journey toward readiness. But first, Webb had to reach its final destination, a specific point in space that was chosen for reasons that go beyond simple orbital mechanics and touch on something almost philosophical about what it means to build an observatory designed to last decades. The location Webb travels to is one that no spacecraft had occupied for scientific purposes before, and the reason it was chosen reveals something unexpected about the relationship between cold, distance, and the ambition of what this telescope was built to do. Webb does not orbit Earth. Most space telescopes, including Hubble, orbit at a few hundred miles above the planet's surface, well within the range of servicing missions. Astronauts visited Hubble 5 times to repair instruments, replace components, and extend its life. That option was always part of the plan. Webb was placed 1 million miles from Earth in a location called the second Lagrange point. At that distance, no human spacecraft has ever traveled for a servicing mission. No astronaut can reach it. If something breaks on Webb, the options are limited to whatever commands engineers can send from the ground. If something breaks in a way that cannot be fixed remotely, that component stops working permanently. The choice of this location was not made carelessly. The second Lagrange point has a specific property that makes it almost uniquely suitable for an infrared observatory. It is positioned directly behind Earth from the perspective of our star, so that Earth and the Moon are always on the same side as the star. The heat shield deployed between the telescope and all 3 of those heat sources simultaneously can keep the telescope cold indefinitely without constantly repositioning. At any other orbit, the geometry would change constantly. The telescope would need to continuously adjust its orientation as it moved through different angles relative to the heat sources. The heat shield could not do its job reliably. The mirror would warm and cool in cycles, and the science would suffer. At the second Lagrange point, Webb sits in a permanent cold shadow of its own making. It orbits that point in a slow loop, always keeping the shield between itself and all sources of heat simultaneously. The laws of orbital mechanics and the geometry of the solar system conspire to create exactly the stable, cold, consistent environment that an infrared observatory requires. The cost of this location is the impossibility of servicing. Engineers knew this when they chose it. They knew that every component on Webb had to be reliable enough to last the full mission lifetime without human intervention. That constraint shaped every design decision, from the redundancy built into the deployment mechanisms to the testing protocols that took years longer than they might have otherwise. It also meant that the 29 days of deployment, the 300 points of failure, the heat shield unfolding, the mirror wings locking, were all one-time events. If any of them had failed, the options were not fix it or return home. The option was watch the most expensive scientific instrument in history become an inert golden sculpture orbiting the second Lagrange point indefinitely. The deployment succeeded. Webb arrived at its operating location, the heat shield deployed correctly, and the telescope began the long process of cooling to its operating temperature. Then came the 2 weeks that nobody had properly prepared themselves for. 2 weeks of complete silence. No science, no images, no data worth publishing. Just waiting, watching temperature readouts drop degree by degree toward the threshold at which the instruments could finally open their eyes. And what they saw, when they finally did, was something that even the most optimistic scientists on the team had not quite allowed themselves to believe was possible. July 12, 2022. 6 months after launch, the James Webb Space Telescope had been cooling, aligning, and calibrating for months. The mirror segments had been nudged into their final positions by the actuators, 1 nanometer at a time, until they acted as a single unified surface. The instruments had been powered on and tested. The team on the ground had verified every system, run every check, and confirmed that the telescope was performing better than any of their pre-launch models had predicted. Now it was time to release the first images to the world. The first image shown publicly was a deep field, a long exposure pointed at a patch of sky that, to the naked eye or any ordinary camera, appears completely empty, just darkness. Webb stared at it for 12.5 hours, collecting every infrared photon that fell on its 21-foot gold-coated surface. When the processed image appeared on screens at the public event, it contained thousands of galaxies. Thousands, in a region of sky smaller than a grain of sand held at arm's length. Galaxies of every shape, spirals, ellipses, irregular smears, arcs, distorted into curves by the gravitational bending of light as it passed massive galaxy clusters on its way to the telescope. Some of the objects in that image emitted their light when the universe was less than 1 billion years old. They existed before our own galaxy had settled into its current form, before our star had ignited, before the rocky material that would become Earth had even begun to gather. Their light, stretched by 13 billion years of travelling through an expanding universe, had arrived at Webb as infrared radiation. The gold mirror had caught it, the instruments had decoded it, and the image on the screen was showing humanity a view of the universe that had never been seen before. Scientists in the audience had spent years, in some cases decades, working toward this moment. Several of them later described the first time they saw the full image as a kind of silence, a moment where the enormity of what they were looking at made words feel inadequate. This is confirmed. The image was real, the distances were measured, the galaxies were there. This is not a simulation or an artist's impression. It is a direct photograph of the universe as it was billions of years ago, made possible by a 21-foot beryllium mirror coated in 2 ounces of gold, operating at -364 degrees Fahrenheit, 1 million miles from the planet that built it. But the first images were just the beginning. As scientists began analyzing the data in detail, they found something in those deep field observations that they had not expected. Something that went beyond beautiful. Something that forced a serious conversation about whether the best models of how galaxies form and grow were actually correct. The universe in those images did not look the way the models said it should, and the discrepancy was not small. It was visible in image after image, in object after object, in a pattern consistent enough that researchers began using a phrase that had never been spoken seriously in professional cosmology before: universe breakers. What Webb found in the deep field, and what it means for everything we thought we understood about how the universe assembled itself, is the next chapter in this story, and it is stranger than almost anyone predicted. ***, JWST can see 13 billion years back in time. The deep field image from July 2022 was beautiful. It was also, underneath the beauty, deeply unsettling. As scientists began pulling individual objects from the image and analyzing their light, a pattern emerged that did not match the models. Not in a small way, in a way that required serious papers, serious conversations, and eventually a term that spread from astronomy preprints into general headlines: universe breakers. Here is the problem. The standard model of cosmology, the framework that describes how the universe evolved from its beginning through to the present day, makes specific predictions about what the early universe should look like. In the first few 100 million years after the beginning, matter was distributed relatively evenly. Gravity was slowly pulling gas clouds together. The first stars were igniting inside those clouds. Galaxies were beginning to assemble, messy and small and irregular, accumulating mass slowly over billions of years. Building a massive, well-organized galaxy takes time. You need generations of stars to form, burn through their fuel, explode, and scatter heavier elements back into the gas. You need those elements to cool and collapse into new stars. You need gravity to pull billions of these stellar systems into a coherent rotating structure. According to the best models, that process cannot happen in a few 100 million years. It takes billions. Webb pointed at the early universe and found galaxies that looked like they had already done all of that. Massive, bright, structured, some containing stars that appeared to be older than the galaxies around them had any right to be. This is a confirmed observational finding. The objects are real. The distances have been verified through spectroscopy, measuring the precise stretching of specific known spectral lines to confirm how far the light has travelled. The galaxies exist where they appear to exist, at the distances that make them as old as they look. What is not yet confirmed is what they mean. Several explanations are being tested. Perhaps the standard model underestimates how quickly the first generation of massive stars could have formed from pure hydrogen and helium gas, without the slower processes that later stellar generations require. Perhaps early galaxies could accumulate mass through mechanisms that current simulations do not capture well. Perhaps there is something genuinely new in the physics of the early universe that the models are missing. None of these explanations has been confirmed. All are under active investigation. This is an open mystery. What is clear is this: Webb has handed cosmologists a problem they cannot currently explain away. Every time a new deep field observation comes in, the anomalous objects are still there. They have not turned out to be measurement errors. They have not resolved into something more comfortable. They are real, and they are strange, and they are forcing a rethinking of some assumptions that have been treated as settled for decades. For the scientists who spent their careers building those models, the Webb data is both exciting and uncomfortable. It is exactly the kind of result that drives science forward. A clean observation that the best existing theory cannot fully account for. But the universe breakers are not even the most personally significant thing Webb has found, because while it was staring at the ancient universe, it was also being pointed at something much closer, at worlds orbiting nearby stars, and at the question of whether any of those worlds might have something in common with the one we are standing on. When a planet passes in front of its star, something subtle happens to the starlight. Some of that light does not travel straight to the telescope. It grazes the edge of the planet and filters through the outermost layers of the atmosphere before continuing onward. Different gases in that atmosphere absorb different specific wavelengths of light as it passes through. By the time the filtered light reaches the telescope, certain wavelengths are missing or weakened. The pattern of those missing wavelengths is a chemical fingerprint. Read it carefully, and you know what the atmosphere is made of. This technique is called transmission spectroscopy. It had been used before Webb, but never with the sensitivity that an infrared telescope of this size and precision could achieve. Earlier instruments could detect the presence of certain molecules with moderate confidence in the atmospheres of large, close gas giants. Webb can detect dozens of molecules simultaneously in smaller planets at greater distances, with enough precision to distinguish between competing chemical interpretations. The first major demonstration of this came with a gas giant called WSP-96b. It orbits a star about 1,100 light-years away, making it completely unreachable by any spacecraft humans could build in the foreseeable future. Webb pointed at it as its star's light filtered through its atmosphere and produced a spectrum so detailed that scientists identified water vapor, carbon dioxide, and the signatures of clouds and haze simultaneously in a single observation. Carbon dioxide, confirmed, in the atmosphere of a world over 1,000 light-years away. That is confirmed science, peer-reviewed and published. It was the first unambiguous detection of carbon dioxide in an exoplanet atmosphere, but the planet that has drawn the most attention and the most careful scientific language is one much closer to home. 40 light-years away, a star called TRAPPIST-1 hosts 7 rocky planets roughly the size of Earth. 3 of them orbit within the range of distances where liquid water could theoretically exist on their surfaces. Webb has been observing these planets repeatedly. The results so far are mixed. One of the inner rocky planets appears to lack any significant atmosphere, its dayside temperatures suggesting bare rock with no air to redistribute heat. Others are still being analysed. The 3 potentially habitable ones have not yet been fully characterised. This is a theory still under investigation, not a confirmed finding either way. Then, in 2023, a research team reported something that spread far beyond astronomy journals. In the spectrum of a planet called K218b, a world about 120 light-years away, they detected a possible signal for a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine organisms, phytoplankton mainly. If that signal is real and is confirmed by further observations, it would be the first chemical indicator of possible biological activity ever detected beyond our solar system. This is currently a theory. The signal is uncertain. Scientists are cautious, and rightly so, but it is real enough that follow-up observations have been prioritized, and the scientific community is watching the data carefully. A gold mirror, 100 nanometers thick, floating 1 million miles from Earth, may have caught the first faint whisper of life beyond our world. Or it may have caught something that mimics that whisper through purely chemical means. The answer requires more time and more data, but the capability to even ask this question is entirely new. And the next discovery Webb made went in a completely different direction, towards something that cosmologists had been quietly worried about for years before Webb ever launched. Before Webb launched, cosmology already had a problem it could not solve: a disagreement between two of its most reliable measurement methods, persistent for years, growing larger as the data improved, and stubbornly refusing to go away no matter how carefully scientists checked their work. The problem is called the Hubble tension, and understanding it requires knowing that there are two completely independent ways to measure how fast the universe is currently expanding. The first method looks at the nearby universe. Astronomers observe a type of exploding star called a Type 1a supernova. These explosions have a known peak brightness, which means their distance can be calculated precisely from how bright they appear. By measuring how fast galaxies containing these supernovae are moving away, scientists can calculate the current expansion rate directly from observation. The second method looks at the early universe. In the first 380,000 years after the beginning, the universe was a hot, dense plasma in which light and matter were locked together. When that plasma cooled enough for atoms to form, the light was released and has been traveling freely ever since, filling all of space as a faint microwave glow detectable from any direction. The precise pattern of that glow encodes the conditions of the early universe, and from those conditions, scientists can calculate what the expansion rate should be today, based on how the universe has evolved since then. These two methods give two different numbers. The disagreement is roughly 8 to 9%. That sounds small. In cosmology, measuring the same fundamental quantity two independent ways and getting answers that disagree by 8% is not a rounding error. It is a crisis. One possibility is that one of the measurement methods has a systematic error hidden somewhere in its assumptions. Astronomers have spent years checking every step of both methods, looking for the mistake. They have not found one that accounts for the full discrepancy. Another possibility is that the standard model of cosmology is missing something real, some physical process operating in the early or late universe that the model does not include, and that shifts the expansion rate in a way that explains the gap. If that is the case, it would represent a genuine gap in our understanding of how the universe works at a fundamental level. Webb was expected to help resolve this. Its precision would allow much more accurate measurements of the supernova distance ladder, potentially revealing a hidden error in the nearby universe method. Instead, Webb made the tension worse. It confirmed the nearby measurements with higher precision than had been achievable before, showing that the numbers from that method were not drifting due to instrument limitations. The disagreement is real. The gap is not getting smaller as the data improves. If anything, better data is making the discrepancy more statistically solid. This is confirmed. The Hubble tension exists and has not been explained. This is an open mystery. What causes it? The possibilities range from a hidden measurement bias that nobody has identified yet, to genuinely new physics that the standard model of cosmology does not contain. Webb has not solved this problem. It has confirmed that the problem is real, and that solving it will require either finding a specific error in the existing methods or revising the theoretical framework that has been the backbone of modern cosmology for decades. But as unsettling as that tension is for cosmologists, what Webb found when it looked at the most ancient and massive objects in the early universe was something that unsettled a different group of scientists entirely. In the deep field images, among the thousands of galaxies at every distance and age, scientists noticed a category of objects that did not fit the expected picture of the early universe. They were compact, extremely bright, extremely red, present in far greater numbers in the first billion years of cosmic history than the models predicted. Researchers named them, informally, little red dots, and as follow-up observations accumulated, the picture they revealed became more and more difficult to explain. Many of these little red dots appear to be small early galaxies with supermassive black holes at their centers. Black holes that are not merely large, but disproportionately large relative to the galaxies around them. In the present-day universe, the ratio of a central black hole's mass to the mass of its host galaxy follows a fairly consistent pattern. The black hole is always much smaller than the galaxy. It is a tiny but enormously dense object at the core of a much larger structure. In the early universe objects Webb detected, that ratio is inverted, or at least severely distorted. The black holes appear to be a much larger fraction of their host galaxy's total mass than anything seen in the modern universe. They grew to hundreds of millions of times the mass of a star within just a few 100 million years of the beginning of everything. Standard models of black hole growth say this should not happen. Black holes grow by pulling in surrounding gas, a process limited by how fast that gas can fall inward without the radiation pressure from the infalling material, pushing other gas outward and shutting off the flow. This limit, called the Eddington limit, constrains how quickly a black hole can grow under normal conditions. To reach the masses Webb is observing, in the time available in the early universe, the growth rates would have had to exceed that limit repeatedly, or black holes would have had to start from a much larger initial size than the standard models produce. This is a confirmed observational anomaly. The objects are real. Their properties are estimated using well-established methods for interpreting the light from active galactic nuclei. The anomaly is that their numbers and their masses do not match what current simulations of early universe black hole formation predict. Several explanations are being tested. Perhaps the very first stars, formed from pure hydrogen and helium without any heavier elements, were far more massive than stars today and collapsed directly into much larger black holes when they died. Perhaps in the dense conditions of the early universe, black holes could occasionally grow faster than the Eddington limit through mechanisms that are rare or absent in the present-day universe. Perhaps some of the apparent mass is being overestimated due to the extreme brightness of the active nuclei overwhelming the light from the surrounding galaxy. None of these explanations is confirmed. All are under investigation. This is an open question in astrophysics, one that Webb has made sharper and more urgent simply by showing how common these objects are. The count keeps growing with every new deep field observation. The early universe, it turns out, was far more active and far more extreme than any simulation had captured, and every new Webb image makes the gap between observation and theory a little harder to dismiss. But Webb has not only been looking at things that break models, it has also been looking through something that has blocked our view of some of the most important places in the universe for the entire history of astronomy. And what it found on the other side of those walls changed the picture of how stars are actually born. Space between the stars is not empty. It is threaded with cold, thin clouds of dust, grains of carbon, silicate minerals, and ice-coated particles too small to see individually but collectively dense enough. Across sufficient distances, to form walls that block visible light as completely as a closed door. Behind those walls, some of the most energetic and scientifically important processes in the universe are happening. And for the entire history of optical astronomy, those processes were hidden. Star formation happens inside dust. A cloud of gas and dust collapses under its own gravity, spinning inward, heating up, until the pressure and temperature at the center become high enough to ignite nuclear fusion. A star is born. But the whole process, from collapsing cloud to ignited star, is buried so deeply inside dust that a visible light telescope looking at a star-forming region sees nothing but darkness where the action is. Infrared light passes through dust far more easily than visible light does. The longer wavelengths of infrared scatter off dust particles less than shorter visible wavelengths, for the same physical reason that red light cuts through fog more effectively than blue light. Webb's gold mirror, tuned to infrared across its full operating range, can see straight through the dust walls that have blocked our view of star formation for generations. The most famous demonstration of this is the Pillars of Creation. This structure, a set of towering columns of gas and dust inside a star-forming cloud about 6,500 light-years away, was first photographed by the Hubble Space Telescope in 1995 and became one of the most iconic astronomical images ever taken. In visible light, the pillars are dark and dramatic, backlit by the glow of the nebula behind them, with their surfaces sculpted by radiation from nearby young stars. Webb photographed the same structure in infrared. The result was completely different and completely new. The dust became translucent. Inside the pillars, embedded in the dense gas that visible light could not penetrate, newly forming stars appeared for the first time. Protostars, still wrapped in their birth cocoons of gas and dust, glowing in infrared, caught in the act of formation at a stage that had never been directly observed before. This is confirmed science. The infrared images are real. The embedded young stars are real. Webb showed us something that was physically present in the Pillars of Creation during every Hubble observation, but invisible to Hubble's instruments. The same infrared transparency applies to the core of our own galaxy. The center of the Milky Way is buried under so much dust that visible light telescopes see almost nothing of it. Webb stares straight through to the galactic center and has already revealed unexpected structures in the star-forming regions there, including elongated filaments of glowing gas that nobody predicted and which are still being analyzed. Webb has turned dust from an obstacle into something almost like a window that, until this telescope existed, was a wall. But it is not only ancient light and star-forming dust that Webb has illuminated. When scientists turned the telescope toward worlds far closer to home, planets in our own solar system that had been studied for decades, Webb showed them things that generations of observations had missed, and some of what it found there was genuinely unexpected. Webb was built to see the edge of the observable universe. That is its primary purpose. But its gold mirror collects infrared light from whatever it is pointed at, nearby or distant, with the same precision and sensitivity. When astronomers pointed it at planets in our own solar system, they found things that decades of prior observation had not revealed. Jupiter was the first major solar system target. The results were striking in ways that surprised even the scientists who had spent their careers studying this planet. Webb's infrared view showed auroras at Jupiter's poles in detail and intensity that exceeded all expectations. These auroras are driven by charged particles flowing along the planet's enormous magnetic field and striking the upper atmosphere. In infrared, the scale and structure of these features was far more complex than what visible light instruments had captured. The energy involved exceeded what the existing models of Jupiter's magnetosphere had predicted. Webb also revealed new detail in Jupiter's atmospheric bands and its famous storm systems, showing temperature variations and chemical distributions at different altitudes that will take years of analysis to fully understand. The data is rich enough that researchers who had no particular interest in Jupiter before Webb launched are now building careers around the observations. Saturn's rings showed something unexpected as well. Webb's infrared sensitivity revealed thermal structure within the rings, variations in temperature between different ring regions that correspond to differences in the size and composition of the particles making up each zone. The rings have been studied since the 17th century, and this is information that no previous instrument had been capable of extracting. The most surprising solar system result came from Neptune. Webb detected auroras there for the first time ever. Neptune's magnetic field is tilted at an extreme angle relative to its rotational axis and offset from the planet's center, creating a complex and asymmetric auroral pattern unlike anything seen around any other planet in the solar system. Previous telescopes had looked for Neptunian auroras without success. Webb found them in infrared on its first attempt. These solar system observations were not what Webb was designed for. They are secondary science, observations made during time between the primary deep field and exoplanet programs, but they demonstrate something important about the telescope's capabilities. Webb is not a specialized instrument that can only answer one type of question. It is a general-purpose infrared observatory of unprecedented power, and almost anywhere it looks, it finds something that the previous generation of instruments could not reach. Every solar system observation also serves a direct scientific purpose beyond the local discoveries. Understanding how Jupiter's atmosphere behaves in infrared helps calibrate the interpretation of infrared observations of gas giant exoplanets orbiting other stars. Understanding Neptune's auroral geometry informs models of magnetic field interactions in planets orbiting dim red stars, where auroral activity may be far more intense and may affect whether those worlds can hold on to their atmospheres. Webb's view of our own neighborhood is a training ground for its view of the broader universe. But there is one aspect of Webb's capabilities that goes beyond what it was even originally designed to do, and it involves what happens when you combine its infrared precision with something called active mirror control, something that lets the telescope correct its own shape in real time from 1 million miles away. In 1990, the Hubble Space Telescope launched with a flaw in its primary mirror. The surface had been polished to the wrong shape by an error smaller than 1/50th the width of a human hair. The images it returned were blurry. An instrument that had cost billions of dollars and taken more than a decade to build was, in its core scientific function, broken. It took 3 years and a spacewalking repair mission to fix it. Astronauts installed corrective optics, essentially a precise set of lenses that compensated for the mirror's wrong shape, the way a pair of glasses corrects a human eye. Hubble recovered and went on to transform astronomy. But the initial failure was a defining moment in the history of space science, and the lesson it taught shaped every decision made in Webb's design. Webb cannot be repaired by astronauts. Its location 1 million miles from Earth puts it permanently beyond reach. So the designers built the correction capability directly into the telescope. Behind each of the 18 primary mirror segments, 6 small motorized positioners called actuators are attached to the mirror's back surface. Each actuator can push or pull its attachment point by steps as small as a few nanometers. By commanding different actuators by different amounts, engineers can bend each mirror segment into a slightly different shape, adjusting its curvature with extraordinary precision. This system serves 2 purposes. The first is alignment. After Webb's mirror unfolded in space and cooled to operating temperature, the 18 segments were not perfectly positioned relative to each other. Each needed to be nudged into exactly the right orientation so that all 18 acted as a single unified surface. The actuators made this possible, adjusting each segment by nanometers at a time over a period of months until the alignment met specifications. The second purpose is correction. If a mirror segment's shape drifts over time due to the slow thermal changes of the space environment, The actuators can compensate. If a segment was polished to a shape that is subtly off from ideal, the actuators can bend it toward the correct form. The corrections possible are small, a few nanometers of adjustment across a mirror surface measured in feet. But at the wavelengths Webb works in, a few nanometers of correction can make the difference between optimal performance and degraded image quality. When the initial alignment was completed in early 2022, the mirror's optical performance exceeded every pre-launch prediction. The wavefront error, which measures how precisely the mirror surface matches its mathematically ideal shape, came in better than the most optimistic projections the team had published before launch. This is confirmed. Webb's mirror performs better than it was required to. It does not merely meet its specifications, it exceeds them, which means every instrument behind it is receiving cleaner, sharper, more complete light than the mission designers had formerly promised. The Hubble mirror failure taught the astronomical community that optical perfection cannot be assumed. It has to be verified redundantly, and where possible, corrected. Webb embodies that lesson in its most literal form. It carries the ability to adjust its own vision remotely from the ground after the moment of launch has passed and no human hand can ever touch it again. That ability has implications not just for how Webb works today, but for how the telescopes that come after it will be designed. Because Webb has proven that a segmented, actively controlled mirror can exceed the performance of a solid mirror of comparable size, and that changes what is considered possible for the observatories of the future. Webb is the most powerful space telescope humanity has ever built, and it has limits. It sees infrared light. That is both its greatest strength and its fundamental constraint. The science questions it cannot address are not failures of execution. They are consequences of physics. Different questions require different tools. Webb does not see visible light with high efficiency. Its mirror and instruments are optimized for wavelengths longer than what the human eye detects. For the sharp, high-resolution visible light imaging that made Hubble iconic, Webb is not the right instrument. Its infrared images have a resolution limited by the longer wavelengths it works in. Two objects that Hubble could separate as distinct sources might blur together in Webb's infrared view. Webb also cannot observe the entire sky. Its heat shield permanently blocks half the celestial sphere from view. Any object that lies too close to the direction of our star, or too close to the plane of the solar system, where the combined light of countless small bodies creates a diffuse infrared glow called zodiacal light, is difficult or impossible for Webb to observe cleanly. Some of the most interesting objects in astronomy are in those regions, and Webb simply cannot reach them. And Webb, for all its cold stability engineering, will not operate forever. The thruster fuel that maintains its orbital position at the second Lagrange point is finite, based on the precision of the launch trajectory, which placed Webb more accurately than the minimum required. The fuel budget extends well beyond the original 10-year mission life. Current estimates suggest the telescope may operate into the late 2030s, but at some point the fuel will run out, the position cannot be maintained, and the mission will end. When that happens, Webb will not be brought home. There is no retrieval mechanism for an object at that distance. It will continue orbiting the second Lagrange point indefinitely, its instruments silent, its gold mirror still reflecting whatever infrared light falls on it in the cold and dark. These limitations are not complaints. They are the reason the next generation of telescopes is already being designed and, in some cases, built. On a mountain in northern Chile, construction is underway on what will be the largest optical telescope ever built on the ground. Its primary mirror is 128 feet across, nearly 6 times the collecting area of Webb. It uses adaptive optics, systems that correct for atmospheric blurring in real time, to achieve resolution sharper than any space telescope in visible light. It is designed to directly image the light reflected from rocky planets around nearby stars, something Webb cannot do. In space, a telescope called the Nancy Grace Roman Space Telescope is scheduled to launch in 2027. Its mirror is comparable in size to Hubble's, but its field of view is 100 times larger. It will map the universe at scales that would take Webb or Hubble decades to cover. Beyond that, concept studies are underway for a future flagship observatory specifically designed to search for biological signatures in the atmospheres of Earth-like planets around nearby stars. A telescope built around the single question that Webb has made sharper and more urgent with every observation it returns. Webb is not the end of anything. It is a demonstration of what becomes possible when you accept the full strangeness of the physics and build an instrument that matches it. The telescopes that come next will be stranger still, and they will be built because of what Webb showed was achievable. $10 billion, 25 years from initial concept to first light, thousands of engineers, scientists, and technicians across 14 countries, 3 major space agencies, and one telescope that had to work perfectly the first time, with no possibility of a second chance. The cost of Webb is a number that generates debate wherever it is mentioned. $10 billion is an amount that invites comparison. It is roughly the cost of a major infrastructure project, or a significant military procurement, or the annual budget of a mid-sized government department. Is it worth it? The answer depends entirely on what you think seeing the beginning of the universe is worth, and, more practically, on what the scientific output has actually been. By any measure of scientific productivity, Webb has already exceeded expectations. In its first 2 years of operation, it produced more peer-reviewed papers than Hubble did in its first 5 years. It answered questions that had been waiting decades for the right instrument. It opened new questions that nobody had even thought to ask before the data arrived. It detected carbon dioxide in an exoplanet atmosphere, confirmed the Hubble tension is not a measurement error, revealed star formation inside dust pillars, found auroras on Neptune, and showed the world galaxies that existed before our own galaxy was born. But the cost also reflects something about what it takes to do science at this level of ambition. Webb's budget grew significantly from its original estimates, not because of waste or poor management, in any simple sense, but because the engineering challenges turned out to be harder than the initial projections assumed. Cryogenic polishing of beryllium at the required precision took longer than expected. The heat shield deployment mechanism required years of additional development and testing. Every component that had to work flawlessly, with no repair option, had to be tested to standards that cost more time and money than standard aerospace practice. The lesson the astronomical community took from Webb's development is not that such telescopes should not be built. It is that the initial cost estimates for projects at this level of technical difficulty should be treated as minimums, not ceilings, and that the scientific return over decades of operation justifies the investment, even when that investment turns out to be larger than originally projected. Webb's datasets will be analysed for decades after the telescope itself stops operating. Graduate students who are currently in primary school will build careers around observations that Webb is making right now. The data does not expire when the fuel runs out. It accumulates in archives and continues yielding discoveries as new analytical tools and new theoretical frameworks allow scientists to see things in the data that were not visible before. This is how the most productive scientific instruments work. Hubble's data, collected over more than 3 decades, is still producing published results today. Webb's archive, already richer per unit time than Hubble's, will follow the same trajectory. The cost of seeing 13 billion years back in time, it turns out, is not primarily measured in dollars. It is measured in the willingness to solve problems that have no precedent, to build things that have never been built before, and to accept that the price of the answer to a genuinely new question cannot be accurately estimated in advance. What those answers have revealed about the structure of the observable universe, and about our place in it, is the final chapter in this part of the story, and it ties everything back to the title of this video in a way that goes deeper than the engineering. The title of this video makes a promise that the reason Webb can see 13 billion years back in time is stranger than you would expect. Most people, when they first encounter this fact, assume the answer is simply a very big mirror, and a big mirror is part of it, but it is the smallest part of the actual answer. The real reason is this: the universe itself changed the light, and that change forced every other decision. 13 billion years ago, the earliest galaxies were emitting visible light, ordinary photons, the kind human eyes detect, leaving stars and clouds of glowing gas and travelling outward in all directions. Some of that light happened to be travelling in the direction that Earth would eventually occupy, toward a point in space where, billions of years later, a small rocky planet would form, and billions of years after that, a species would develop that wanted to see where it all began. But the universe those photons were travelling through was expanding continuously in every direction at once, and as the space between the photons and their eventual destination stretched, the photons stretched with it. Their wavelengths grew longer, their energy decreased. By the time those photons completed their 13 billion year journey and reached the solar system, they were no longer visible light at all. They had become infrared radiation, heat, the kind of energy that warms your face when you hold your hand near a radiator. You cannot see infrared light with your eyes. Neither can a camera film or a CCD sensor optimized for visible wavelengths. Neither can the Hubble Space Telescope. The ancient universe was radiating information in a language that the best telescope ever built until that point was not equipped to read. This single physical fact, that expanding space stretches light into invisibility, made it necessary to build an infrared telescope. And building an infrared telescope at the scale required to detect 13 billion year old signals made it necessary for the mirror to be cold, and cold made beryllium necessary, and beryllium made gold necessary, and the size of the mirror made folding necessary, and folding made the 29-day deployment sequence necessary, and the deployment sequence made the impossibility of repair a calculated risk that had to be accepted. Every strange engineering choice in Webb's design traces back to one strange physical fact about the nature of the universe. The universe is expanding, and expansion has consequences that ripple forward through every decision a telescope designer makes, all the way down to the choice of what metal to coat a mirror with and how many nanometers thick that coating should be. Webb does not see the past because it is powerful. It sees the past because it was designed specifically around the way the universe changes light over cosmic distances. It was built to receive a message in the form that the universe actually sends it, rather than the form we find most convenient to detect. That is the stranger truth. The universe wrote the engineering specifications. The physicists read them. The engineers built what the specifications required. And the result is a gold-coated, beryllium-structured, cryogenically cooled, origami-folded, 1 million mile away instrument that has shown us the universe as it was, in the years just after it began, for the first time in the history of intelligent life on Earth. The next 3 chapters take this further, into what those images have revealed about where the universe came from, where it is going, and what it might contain that we have not yet found. Stay with us. Asterisk, JWST, can see 13 billion years back in time, asterisk. Every element in the universe absorbs and emits light at specific wavelengths, not a range, not approximately, exactly. Hydrogen absorbs at one precise set of wavelengths, helium at a different set, carbon, oxygen, water, methane, each has a fingerprint as unique as a human face, written in the specific wavelengths of light they interact with. This is not a modern discovery. Scientists have been reading these fingerprints since the 19th century, when they noticed that starlight contained dark lines at specific positions caused by specific elements absorbing specific wavelengths. By matching those patterns to laboratory measurements, they could determine what distant stars were made of without ever leaving Earth. Webb uses this same principle, called spectroscopy, at a level of sensitivity that changes what questions can be answered. When a planet passes in front of its star, light from the star filters through the outermost layers of the planet's atmosphere on its way to the telescope. The gases in that atmosphere absorb specific wavelengths. By spreading the filtered light into its component wavelengths and measuring which ones have been weakened, scientists can read the chemical composition of an atmosphere that is trillions of miles away and completely unreachable by any spacecraft. Webb's infrared spectroscopy instruments detect dozens of molecules simultaneously with high confidence. Carbon dioxide, water vapor, methane, carbon monoxide, sulfur dioxide, ammonia, each leaves a distinct pattern in the infrared spectrum. Some of these molecules are straightforward products of geological and chemical processes with no connection to life. Others are more interesting. Oxygen in large quantities is almost impossible to maintain in a planetary atmosphere without continuous replenishment. On Earth, the oxygen in the air exists because photosynthesizing organisms produce it constantly. Without life, it would react with surface rocks and disappear within a geologically short time. An atmosphere with high oxygen levels on a rocky planet is a chemical anomaly that would be very difficult to explain without invoking biology. Methane and oxygen together are even more interesting. In the presence of oxygen, methane is quickly destroyed by chemical reactions. If a planet's atmosphere contains both in significant quantities simultaneously, something has to be producing the methane continuously to replace what is being destroyed. On Earth, that something is living organisms. The combination of methane and oxygen together in a rocky planet's atmosphere is considered one of the strongest potential biosignatures scientists know of. Webb has not yet detected this combination on any exoplanet. This is an unknown mystery still to be resolved, but it has detected carbon dioxide unambiguously on one gas giant, potential dimethyl sulfide on one distant world under ongoing analysis, and water vapor in multiple atmospheres. It is building the library of chemical reference points that will make a genuine biosignature detectable when the data eventually arrives. The language every atom speaks has been known for over a century. Webb is the first instrument powerful enough to hear it spoken from across the galaxy, but the molecules Webb hunts for in alien atmospheres are only part of the chemical story it has uncovered. Because while astronomers were analyzing the air of distant worlds, geologists and planetary scientists were pointing Webb at something far more personal: the raw ingredients from which planets, including our own, are assembled. And what they found in those ingredients was not what anyone expected. Before a planet exists, there is a disk. When a young star ignites, the material that did not fall into the star stays behind as a flat, rotating cloud of gas and dust surrounding it. This protoplanetary disk is the raw material from which every planet, moon, asteroid, and comet in that system will eventually form. Dust grains stick together to form pebbles. Pebbles collide to form boulders. Boulders accumulate into planetesimals. Planetesimals, under the force of gravity, grow into worlds. Astronomers have known the general outline of this process for decades. What they have not been able to do until Webb is read the detailed chemical inventory of these disks with enough precision to understand what specific materials are available to the forming planets inside them. Webb has now done this for multiple protoplanetary disks around young stars, and the results have revised the picture of planet formation in ways that matter deeply for the question of how common life-friendly worlds might be. In one disk, around a star in the constellation Taurus, Webb detected a rich collection of carbon-bearing molecules, including ethane, ethylene, diacetylene, benzene, and propyne. These are organic molecules, compounds built around carbon chains. Their presence in the planet-forming zone of a young star system means that the rocky planets assembling there are being built from material that already contains the chemical precursors to the complex carbon chemistry that underlies all known life. This is a confirmed finding. The molecules were detected at high confidence in the disk's mid-infrared spectrum. They were not present in the quantities the models predicted. The planet-forming zone of this star system is richer in carbon chemistry than the equivalent region of our own solar system's early history was thought to be. In a different system, Webb detected evidence of water ice in the cold outer regions of a protoplanetary disk, in the zone where giant planets form. This confirms that water, in frozen form, is available as a building material in the outer reaches of planet-forming systems, available to be incorporated into forming worlds and potentially delivered to inner rocky planets later by impacts. The significance is this: if organic molecules and water ice are common ingredients in protoplanetary disks across the galaxy, then the building blocks of life are not rare accidents that happened only in our solar system. They are standard components of planet formation, assembled into worlds wherever the conditions are right. Webb has not proven that life is common. That question remains open. But it has confirmed that the ingredients are widespread and that the chemical environment in which Earth formed is not as uniquely special as some models assumed. The universe, it appears, is generous with the raw materials. What it is less generous with, or so it seems, is the specific combination of conditions that allows those materials to organize into living systems. Understanding that combination is the deepest question Webb was built to begin answering, and the answer may depend on something Webb has found deep inside the most extreme objects in the observable universe. Objects so dense that they warp the space around them. Objects that should not have been as large as Webb found them to be. Objects that have forced a rethinking of how galaxies themselves are assembled. At the center of almost every large galaxy in the observable universe sits a black hole, not a small one. A supermassive black hole, containing anywhere from a few million to tens of billions of times the mass of a star, compressed into a region smaller than our solar system. Our own galaxy has one. It is called Sagittarius A star, and it weighs roughly 4 million times the mass of our star. For most of its existence, it has been quiet, occasionally pulling in a passing gas cloud or star, but not dramatically active. It is there because the stars near the galactic center orbit far too fast to be explained by anything less massive. In the early universe, many of these central black holes were not quiet. They were consuming enormous amounts of surrounding gas, heating it to extreme temperatures, and releasing energy so intense that the nucleus of the host galaxy outshone all of its billions of stars combined. These active galactic nuclei, in their most extreme form, called quasars, are the brightest sustained light sources in the universe. The relationship between a galaxy and its central black hole is one of the fundamental puzzles in astrophysics. The black hole is tiny compared to the galaxy, and its gravitational influence does not extend far. Yet the masses of the two are consistently connected. Bigger galaxies have bigger central black holes, suggesting the two grew together, influencing each other throughout their shared formation history. Webb has revealed that this relationship was different in the early universe. Among the little red dots, the compact bright objects Webb found in such unexpected numbers in the early universe, many appear to be galaxies where the central black hole is disproportionately massive compared to the surrounding galaxy. The black holes in some of these early objects appear to contain a significant fraction of the total mass of the galaxy itself, a ratio that is almost never seen in present-day galaxies. This is a confirmed observational finding. The mass estimates come from the brightness and spectral properties of the active nuclei, measured using well-established methods, the anomalous ratios are real. Their explanation is an open mystery. One possibility being investigated is that in the earliest galaxies, the black hole formed and grew first, before the surrounding stellar population had time to build up. If the very first black holes formed from the direct collapse of massive gas clouds, rather than from dying stars, as later black holes do, they could have started with much larger initial masses and dominated their host galaxies before those galaxies had time to fill in around them. Another possibility is that some process in the early universe, perhaps the extreme density of gas or the absence of heavier elements that would otherwise slow accretion, allowed these first black holes to grow at rates that would be physically impossible in the modern universe. Either way, the central engines of early galaxies were running hot and growing fast in ways that current models do not capture. Webb has made that clear. The explanation is still being written, and there is one more thing Webb found in the data that nobody expected. Something that connects the ancient universe to the present day in a way that has implications for everything from how stars form to whether rocky planets like Earth are common or rare across the cosmos. The universe is not a random scatter of galaxies floating in empty space. It is structured, organized on scales so vast that the structures are invisible unless you zoom far enough out to see the whole. Galaxies cluster together in groups. Groups cluster into larger clusters. Clusters connect along enormous filaments of gas and dark matter that stretch across hundreds of millions of light years. Between the filaments are vast empty regions, voids, where almost nothing exists. This structure, called the cosmic web, formed from tiny fluctuations in the density of matter in the first moments after the beginning. Regions that were even slightly denser than their surroundings pulled in more matter over time, growing denser still while surrounding regions were drained. Over billions of years, gravity amplified those initial tiny differences into the enormous filaments and voids that define the large-scale architecture of the universe today. Webb has begun mapping this structure at distances that no previous instrument could reach, and the maps are already producing surprises. In the deep field observations, clusters of galaxies are visible at distances corresponding to less than 2 billion years after the beginning. These are confirmed galaxy clusters, multiple galaxies bound together by gravity, existing at a time when the standard model of structure formation suggests such large-scale organization should have been in much earlier stages of development. This is a confirmed finding. The clusters are real. Their distances are verified. Their existence at those distances is not impossible within the standard model, but their frequency and apparent organization is at the edge of what simulations predict, adding another data point to the growing list of observations that the models explain imperfectly. The cosmic web also matters for a more direct reason. The filaments are not just organizational structures, they are highways. Gas flows along the filaments toward the dense nodes where galaxy clusters sit. That gas is the fuel for star formation, the raw material that galaxies need to keep building new stars and growing. How that gas flows, how quickly it arrives, and what happens to it when it reaches a galaxy determine much of that galaxy's history. Webb can detect the infrared signatures of gas in these filaments at distances and sensitivities that were previously impossible. It has already identified evidence of gas streams feeding into early galaxy clusters, confirming that the process of cosmic web-driven galaxy growth was operating in the first few billion years of the universe's history. This matters for the question of life, because the gas flows that feed galaxies determine which stars form, when, and in what chemical environment. The heavy elements produced by earlier stars are spread along the filaments and eventually incorporated into new stars and their planets. The cosmic web is the universe's delivery system for the ingredients of complexity. Webb is tracing those pathways backward through time, following the flow of gas and elements toward their sources across billions of years of cosmic history. And in doing so, it is beginning to draw a map of how the universe became capable of producing the chemical complexity that life requires. Which brings this story to its final question. Not what Webb has found, but what the full picture of the universe it is helping to assemble actually suggests about where we are and what we are doing here. Go back to the deep field image, the one released in July 2022, the one that showed thousands of galaxies in a patch of sky that looked empty. Pick one galaxy at random from that image. It is a smear of light, perhaps slightly distorted by the gravity of something between it and the telescope. It appears unremarkable among the thousands around it. That smear of light is a galaxy containing hundreds of billions of stars. Many have planets. Some orbit at distances where liquid water could exist, and that one galaxy is just one of thousands in a patch of sky smaller than a grain of sand held at arm's length. There are roughly 2 trillion galaxies in the observable universe. If only 1 in a trillion of all the star systems in the observable universe contains a planet with life, there are still roughly 200,000 star systems with life. The universe is so large that even vanishingly small probabilities produce enormous absolute numbers. This is not proof that life is common. The fraction could be 0. There could be something about the emergence of life that is so improbable that it has happened exactly once, here and nowhere else, in 13 billion years of cosmic history. That possibility cannot be ruled out, but Webb has made it significantly harder to argue that the ingredients are rare. Organic molecules in protoplanetary disks, water ice in planet-forming zones, rocky planets in habitable zone orbits around stars of every type, carbon dioxide in exoplanet atmospheres, a possible dimethyl sulfide signal under investigation. The preconditions for life are not scattered randomly through an otherwise hostile universe. They appear to be standard features of planet-forming systems across the galaxy. What the deep field really shows is not just the history of the universe. It is the scale of the opportunity. 13 billion years of star formation, planetary assembly, chemical complexity, and cosmic evolution, repeated across 2 trillion galaxies, all of it visible from a planet so small it does not appear even as a pixel in the image. The James Webb Space Telescope did not go looking for evidence of our significance. It went looking for the light of the earliest galaxies. What it found is a universe so large and so chemically generous that the question of whether life exists elsewhere has shifted from a question about probability to a question about conditions, about what specific combinations of ingredients and time are required, about what we do not yet understand. That is the question Webb has sharpened to a point. The answer will not come from a single image or a single spectrum. It will come from the accumulated weight of data, from Webb and from the telescopes that follow it, each one built on what the previous one revealed. The strange reason Webb can see 13 billion years back in time is that the universe changed the light, but the stranger truth is what that light has started to show. A universe that has had 13 billion years and 2 trillion galaxies worth of time and space to produce something unexpected, and has almost certainly not been doing so in vain. 1 million miles from Earth, a gold mirror is floating in the dark. It has been there for over 3 years. It is minus 364 degrees Fahrenheit. It is made of 18 hexagonal pieces of beryllium, each coated in a layer of gold 100 nanometers thick. The whole coating weighs less than 2 ounces. The mirror cost $10 billion to build, test, and place where it is. It cannot be repaired. It cannot be retrieved. It will never return to the planet that made it. Right now, at this moment, it is pointed at something. A galaxy cluster, a star-forming region, a rocky planet passing in front of its star 40 light-years away. A patch of sky that looks empty, but contains thousands of galaxies at distances that strain the limit of what we can even mean by the word distance. The photons, landing on its surface, left their sources years, thousands of years, millions of years, or billions of years ago. Some left before Earth existed. They survived every hazard of intergalactic space and arrived at a specific gold-coated hexagon at a specific moment, because the geometry of the universe placed that mirror in their path. The mirror does not know this. It does not know anything. It simply reflects what lands on it, without loss, without interpretation, and passes it to the instruments behind it that convert it into numbers, and from numbers into images, and from images into understanding. That understanding has already changed what we know about the universe. It confirmed that early galaxies were stranger and more massive than the models predicted. It found black holes that grew too large for the timeline the models allow. It confirmed that the crack in our measurement of cosmic expansion is real. It showed star birth inside dust pillars that kept their secrets from every previous telescope. It detected the chemistry of alien atmospheres and returned, again and again, to the deep field, building the deepest picture of the early universe ever assembled. Each result has generated new questions. This is how it is supposed to work. The questions Webb has opened will drive the design of the telescopes that follow it. Those instruments will answer some of Webb's questions and open others that we cannot currently anticipate, because we do not yet know what we do not know. Webb's fuel will run out. Eventually, the mission will end. The mirror will go silent. And in the silence, it will continue doing what mirrors do, reflecting whatever ancient light happens to fall on it in the dark. 1 million miles from home, it will redirect without loss toward instruments that will no longer be listening. But the archive will remain. The data will remain. The papers written from that data will remain. And the scientists who grew up watching the first deep field image will spend their careers working through what the gold mirror saw long after the mirror has gone silent. 13 billion years of light, 2 ounces of gold. One question: what is out there, and are we alone in it? The mirror keeps watching, and the answer is getting closer.